Okay, the last lecture was on dimensional analysis and similarity. We went over and came up with, determined a few important non-dimensional numbers that are used in fluid mechanics and fluid dynamics. And we talked about the importance of those simply from the point of view of reducing the number of experimentations that you need to perform and a way to present and collapse the data in terms of just a couple different important parameters, such as Reynolds number, Froude number, Mach number. There are many more, and again you could check those out on Wikipedia. And there's also use of dimensionless numbers in other fields other than fluid mechanics. And last lecture we discussed and alluded to other ways that you can use this to scale from a model to a prototype. Either the prototype could be much larger or much smaller, but the model is going to be something that's useful or small enough that humans can actually use those. So this lecture is on similarity and scaling. Okay, so the very first important type of similarity that is going to need to be achieved is going to be geometric similarity. And there needs to be a geometric similarity between the model and the prototype. So the model is going to be the size that humans can easily use. The prototype is going to be what is going to be the real size of whatever you're trying to build or design. Okay, the very first thing to have geometric similarity between our model and our prototype. Prototype again is going to be the actual size. There's all dimensions have to have the same scale ratio in all three dimensions. So if your model is, or if your prototype is 100 by 100 by 100, you want to create a model, you have to scale that down to 1/10. It'll have to be 10 by 10 by 10. So all dimensions need to scale to the same ratio. So if I have, let's say that this is 1 by 2 by 0.1, and I want to create this to a 0.1 by 0.2, it has to be 0.01 thick. So everything has to scale to the same ratio. So all angles and flow directions and orientation with the surroundings need to be the same. So for instance, if in your model flow direction is to the x direction, and this we'll use as marker as a model of a submarine. If this is going to be in the flow and it's going to be moving along to it, your real submarine has to have the flow head on. If you do your experiments where submarine is perpendicular to the flow and then your prototype is parallel to the flow, you're not going to have geometric similarity. Just like also, if this was to represent your airfoil, if it was off at a degree of 20 degrees, your prototype would have to have, it would be valid for an angle of 20 degrees. So, and it has to be all angles. So the angle doesn't scale, but the angle has to be the same between the model and the prototype. And it has to be in the same flow and the same surroundings. So that's where your model design or experiment will be similar to the prototype. Prototype can be larger or smaller, and to have this, you're going to have the very first part is geometric similarity between your model and your prototype. So everything has to scale, angles need to be the same, and flow directions relative to flow, and the surroundings need to be all similar. All points need to be the same relative location. So again, when you scale it, if this cap part is 1/10 of the way down, it needs to be 1/10 on your prototype. The same ratios. Okay, so once you create a model that's going to be similar geometrically to your prototype, the next thing that you want to have is kinematic. So kinematic is going to be motion. Kinematic, if you've taken a physics class, you have your kinematic equations for constant acceleration. So kinematic equations represent distance, velocity, and acceleration. Distance per time is going to be your velocity. Velocity per time would be your acceleration. So if you had a physics class, kinematic equations are going to represent motion. That's going to be the representation of the kinematics. So the motion, the kinematics have to have similarity. So, relative fluid particles are located at relative locations at relative times. That's going to be velocity. So, to have kinematic similarity, you also are required to have geometric similarity. So that is required. So the very first one is to have geometric similarity. Then the goal is to get kinematic similarity. The last is dynamic similarity. Dynamic uses the kinematic, so dynamic is going to be the forces that are acting upon your model to scale to your prototype. So things that need to be looked at are compressible flow. So when you have compressible flow, Reynolds number and Mach number are important to have similarity between your model and your prototype. If you have incompressible flow, so if you have incompressible flow and let's say no free surface, you just have to have the Reynolds numbers between the model and the prototype be the same. If you have a free surface, and it's incompressible, Reynolds number, Froude number, and where applicable, Weber number and cavitation. So the demonstration where we had the mixer, you'd have to have cavitation taken into account. And again, for dynamic similarity, kinematic and geometric similarity are required. So, to have our non-dimensional numbers between the prototype and the model, they have to be equal. So let's go through an example of where this would be the case. Okay, the example that we want to look at is the desire to determine the prototype, the actual real size velocity where of a submarine that has a diameter of 10 meters. So what does that real velocity need to be to have similarity? If a scale model that's going to be 1/100th of that size. So everything has to scale to 1/100th. So the diameter as well as the length of the model. So this is just a simple representation. Let's say that this would be the model. And again, if this is going to be 10 meters, we went over that this is essentially 1 meter. Multiply that by 10, you're going to have an enormous size submarine. So that would be difficult to perform experiments on. But if you have something that's going to be represented by this marker that you can perform your experiments on in a lab or in a simple little chamber that you can perform similarity experiments on. So you have to scale everything down. So a scale model is used of 1/100th of the size and studied in the following way. So the velocity of the stream going over the model, this is going to be the prototype, is going to be 0.3 meters per second. So put this marker in a chamber and run water over it or past it at 0.3 meters per second. That's going to be the velocity that the model is going to be running at. And let's say the fluid properties for the model, the viscosity is going to be 1.5 PA seconds. Again, that's going to be of the model. And the density of the model, let's say, is going to be so the model is going to have water that has this viscosity and this density, and the water is going to be flowing over the model at a rate of 0.3 meters per second. So as long as we've guaranteed that the model scales down to the prototype, we have geometric similarity. And as long as we keep the angle to be 0 into the flow, we have, again, maintained our geometric similarity. But now let's have dynamic and kinematic similarity. So to have this, the Reynolds number for the prototype has got to equal the Reynolds number for the model. So again, the goal is to find out what the velocity of the prototype, the real sized submarine, needs to be, given that the model is going to be 1/100th of this length and those sizes, and is going to be performed in a chamber that has the viscosity, the density, and the water flowing at that rate. So let's just go through and calculate what our Reynolds number of the model is going to be. Recall what Reynolds number is. The definition is rho v L over mu. And again, this is going to be for the model. Putting the numbers in, 1263 times by 0.3. The length scale that's going to be important is going to be the frontal profile, which has a diameter of 10. So if we have 1/100th of 10 meters, you'll have the diameter, which will be roughly 0.1 meter. The viscosity that we're using is 1.5, which gives a number of 25.3. That is going to be the Reynolds number based on the frontal diameter of your model. Frontal diameter of your tiny model, this one out in a round circle, that would be the Reynolds number that would be existing on this model, small easy enough for a human to handle, and perform in a reasonable size space. Therefore, to have geometric and kinematic dynamic similarity, the Reynolds number of the prototype has to be 25.3. So the model is 25.3, therefore the prototype, everything has to, when multiplied out for the prototype, has to be 25.3. So we gave you the conditions of the model for trying to find the velocity of the prototype. That is the question. What does the water have to be flowing over it, as well as maybe the submarine moving in that liquid? Okay? So if we give the viscosity, that maybe is going to be seen by that actual prototype in the sea. Let's say that the viscosity .001 PA seconds, and the density is 999 kilograms per meter cubed. So this number needs to be the density, the velocity, the length of the prototypes divided by mu. So solving this for velocity of the prototype. The viscosity of the prototype is going to be C. That's going to be of water by 0.001. And then putting that all in your calculator, you should get the velocity of the prototype to be 2.5 times 10 to the negative 6 meters per second. That would be the velocity of your actual prototype. That's a very slow moving submarine. Therefore, what you would know is you would need to go back and adjust some of the parameters. Designing a submarine to move that slowly is not going to be a very effective submarine. So to go back and to explore where the parameters are going to be useful to what's going to be in the prototype, you can go back and choose a different material to perform your experiments on. You can change your viscosity, you can change the value of the density, and you can change the velocity. So therefore you can change the Reynolds number of the model. So this is the useful way to go through and perform the experiments to have a valid situation for your prototype. Now again, usually you work backwards, and that helps design what you want to have for your model. You have a desired velocity, you have your length, you know what fluid properties you're going to have. That gives you a prototype Reynolds number, and then you back out how to design your model. But this was just an illustrative example to see how to use similarity by equating the prototype and the model Reynolds number. Choosing a liquid that has these properties, and then knowing that the water that the prototype will be operating in to back out what velocity would have to work. So again, that's very slow. You need to come up with a new set of model conditions to represent something that's going to be representative that the prototype will need to have.